Hello, everybody. So this is the review for the plate tectonics, rock, geology, relative dating test that we will have on Friday if you're gold and Monday if you're blue and remote. It will definitely be worth your time if you do this before watching the video, because if you just watch me do it, it's just going to be like sitting in class. So really try to make sure you do the work, and then you can compare your notes to mine to make sure that you're not going off on the wrong direction. So doing this answer key is going to be in parts, just because I don't have enough time to do it all in one sitting. But the layers of the Earth, so that's the first section. So the description of the crust, or the lithosphere is another name for the crust, would be it's solid, it's where we live, it's made of tectonic plates, it's brittle, which means that like it can break, which is why it has broken into plates, etc. Important, where we live, makes mountains, and everything we need for life. I'm not worried that you know like all of these things. I'm just worried that you understand the general idea of these different topics. Okay, the mantle would be thick, gooey, almost solid. It's a plastic layer, so it doesn't break like peanut brittle. It kind of moves more like a silly putty. So maybe I'll include that in my description. Silly putty-like. Importance, it's where the convection currents happen, and it's what drives plate tectonics. So that's what the crust is kind of riding on to as it moves around. The outer core is a liquid layer of iron and nickel. I always spell this word wrong, nickel. And it spins. And the importance is that it gives us the electromagnetic shield around us that protects us from the sun's harmful rays. Sun's high energy rays. And then the inner core is a solid iron, nickel. And we talked about how these also have a lot of the other heavy elements like gold, silver, things like that. It's not just iron and nickel. These are just the most common. It's important. It's the center of our planet. Creates a strong gravity. And that strong gravity can hold our atmosphere and things like this. So those are our different layers of the Earth. Okay, so draw a convection current. Make sure to include a heat source in the drawing and describe the motion of the air. So let's say that there's like a fireplace here. So wherever the heat source is, wherever it's the most hot, that's going to create the stuff above it to have a low density. Now, this could be in the mantle. It could be in water. I'm going to do the air example just because I just put a fireplace here. So above the fireplace, the air is going to rise because it's less dense. And then when it hits, I'm going to make a room here so that I have a top. When it hits the ceiling, that is going to get pushed to the right and to the left. And the reason for that is just because more air is coming up behind it, so it kind of has to get out of the way. So it gets pushed along the edge. When it reaches, so maybe pushed, when it reaches the edge, it's going to start to be much cooler. It's going to be more dense, and then it's going to cause it to sink. So more dense, and the air sinks. This could be in the mantle as well. And then because air is rising here at the center, you can't have nothing here. So this air gets pulled back in order to fill in the empty space here. And then it starts the cycle again. Whoops, cycle. Cycle. I spelled that wrong. All right, so air is rising. It's less dense. When it gets to the top, it gets pushed out of the way, becomes cold, more dense. I didn't add cold on here. More dense, and it sinks, and then it gets pulled back into the bottom. So this could happen in the mantle. It could happen in the air, et cetera, et cetera. All right. Then on the back page, I'm asking you to add convection currents to this picture. So the core is down here, and it's going to heat up the mantle, and it's going to rise at this area because it's less dense. And that's at the divergent boundary. So wherever you have the divergent boundary, that's where the mantle is going to be rising. And then it goes underneath the plates. And eventually when it hits the convergent boundary, that's where it's going to sink back down, back towards the core. So at divergent boundaries, the mantle is rising, and at convergent boundaries, that's where it's sinking back down. So the same thing's going to happen over here. This is a bad convergent boundary, but this is going to sink back in. So you can see I have my convection current here. So this would be cool and more dense. Now, it's important also to note, like, this plate is actually moving this way as well. And it would be getting pushed. If there was a divergent boundary over here, there would be mantle rising and moving this direction. And it's still going to sink at the convergent boundary. So there is more than one convection current going on in the mantle. Anywhere where there's a divergent boundary, we're rising. And anywhere where there's a convergent boundary, we're sinking. So this would also be sinking back down from this direction. All right. Then we have plate boundary types. So divergent, what's happening? The plates are separating. New crust is being created, usually on the ocean floor, though it can be, you can have land split apart. It's just most common at the ocean, on the ocean floor. And a side view sketch would be something like, we have the magma rising, moving underneath it. These would be moving away. And then we have like a mid-ocean ridge. So this is a volcano in here. Okay, so then we have convergent, continental. What's happening at the plate boundary? Plates are colliding. And specifically, they are continental plates that are colliding. What is created? Mountain ranges, no volcanoes. And a side view would be, we have a plate, they're coming together, and they create beautiful, that's a snow cap. Beautiful mountain ranges. Okay, convergent, oceanic, continental. What's happening at the plate boundary? Oceanic crust subducts, don't forget that word, under the continental. Plates are coming together. Woo, woo. Okay, what's created? Volcanoes near the beach. And a side view sketch would look something like this, and water, and then this would be moving this direction, that direction, and it melts here, gerbils up because it's less dense, and creates volcanoes up on the land. Convergent, oceanic. So in this one, both plates want to go down because they're both very dense. So plates coming together. both very dense. What's created are trenches. And the side view is the oceanic wants to go down. The other oceanic also wants to go down, but one of them does get to kind of win. I should have made this longer. So this one goes under. Remember, this is all ocean. This is going to melt, create little volcanoes underwater, and eventually this is going to keep growing over millions and millions of years, and you would actually then get an island above the water. So trenches, but also we can get islands, and that would be like the coast of Alaska or all those South Asian islands, like the Philippines and things like that. Also Japan. So lots of different stuff there. And then at a transform, what's happening at the plate boundary is that the plates are sliding past each other. And what's created there are earthquakes, because the plates are trying to slide, but they don't slide really easy. They get stuck, and then they finally release. That's an earthquake. And we don't experience many because we're not near a transform fault. Or a transform boundary. The closest boundary to us is in the middle of the Atlantic Ocean, that divergent boundary. All right, what is a hotspot? A hotspot is a very hot spot, and it has a direct connection to the mantle, and it does not move. So it's always in the exact same place. And they help to show that the plates are moving because they create island chains that show us the direction of the plate movement. And basically, as the plate moves and sits over that hotspot, it creates an island, and then when it moves off of it, it will create another island. So it can help show the direction of plate movement. Okay. How is a hotspot different from a volcano near a plate boundary? Well, a hotspot is directly connected to the mantle. Whereas the volcano near a plate boundary is basically, like we saw before, it's that plate that's actually melting. So at a boundary, it's not the mantle that's melting, it's actually the plate is melting to become the volcano. All right, in the diagram below, label the area where you'd find divergent, convergent, and transform. So anywhere where you see arrows moving away, that would be divergent, divergent, divergent. There's lots of them all over the place. Divergent. B, oh, I didn't label them right. You get the point. Okay, B is convergent. So somewhere where plates are coming together. So here's one, convergent. Here's another one. Here's another one. Okay, that's enough. And then transform. C, there's one. There aren't a whole lot shown on this map. I mean, there are tons of them all over the world, but this map is pretty simplistic. And then the last question says, what is a subduction zone and why does it occur? So it's a place where one plate is going underneath the other one. And it happens because the oceanic crust is more dense. So it's always going to be the oceanic crust going under the continental. So the oceanic is more dense, and so it will sink back into the mantle. And anywhere where you have the subduction zone, you're going to have volcanoes because as that plate subducts underneath, it's going to melt. All right, page 5. So what evidence do we have that the plates are moving? So this would be from the WebQuest, and just from stuff that we've learned. So the first piece of evidence that people talk about a lot are fossils. There were fossils found, the exact same animal or the exact same plant were found on opposite sides of the ocean, and it is extremely unlikely that they swam or floated across that ocean. So the only way that they could see fossils on different parts of or across the world, basically, is if the land was connected at one point. With no oceans. The second thing that we talked about in that were glacial striations, or like glacial evidence of glaciers in areas that are now tropical. And that's evidence because obviously there are no glaciers in the Bahamas right now. But at one point, the Bahamas and other places on the equator were in much colder areas. So it's clear that they have moved to be in warmer areas now, but a long time ago they were in colder areas. Okay, 3. A third thing that was on that Plate Tectonics WebQuest was the age of the seafloor. And we looked at that Google Earth image, and we saw like the red line in the middle, and then out from that, everything was like the same age going out from that. 4, you could say different features like mountains, volcanoes, etc. Like those things wouldn't be able to exist if we didn't have plate tectonics. So if the plates weren't moving, we wouldn't build mountains and we wouldn't be melting plates to make volcanoes. And then hotspots also give us evidence for the plates moving, and they can help us to see the direction. We already talked about those a little bit. All right, how are igneous rocks formed? Think of it in 2 steps. So first you have to melt a rock, get magma, and then the second step, cool it. Does where an igneous rock cools affect what the rock will ultimately look like, how minerals will be? Yes. If it cools inside, it's called intrusive. And that means that the minerals will be very large, like granite. Whereas if it cools outside, it's called extrusive. So that means that the magma actually exited the volcano. Or exploded. And the minerals are very small. So how you can remember that is that picture that I showed of that mineral cave in Mexico. And it took millions of years, but those crystals were able to grow 36 feet long. So if you give minerals time and space to grow, they can actually grow pretty big. But if you explode them out of the volcano, you won't be able to see the minerals at all. They're still in there, you just can't see them without a microscope, so they're very small. So those would be the 2 vocab words, intrusive and extrusive. What are the similarities and differences in how granite and obsidian form? Both from a volcano, and they were both liquid at one point, but granite cooled slowly inside the volcano, and obsidian cooled extremely fast outside the volcano. So at one point, these 2 could have been in the same exact volcano. They just look a lot different depending on how they cooled down. All right, and then how are sedimentary rocks formed? What are the processes that must go through? Describe it in depth. What actually happens? So you take an old rock and then you weather, which is break the rock. Erosion, which is move the rock. Deposition, which is drop the rock off. Then you have to compact the rock, the sediments. And then the last step is lithification or cementation. It's the same thing. And this part's really important because this is all just like making sediments. This part, it would all be sand. But to turn it into an actual rock, you need to do this part. So this, what's actually happening are there are little minerals that are in the water. And over a long time, those minerals precipitate out and they basically glue the rock together. And that's what we see. That's like if you have hard water and you get the little white stuff on the shower heads, that's just the minerals that are in the water precipitating out. So those are the things that are actually gluing rocks together over millions of years. And you take sand and it gets glued together from all those little minerals.